With all of those announcements out of the way, it is my pleasure to introduce Renée Hlozek for tonight's. Renée is a professor in the Department of Astronomy, and so we're very excited to have her here to tell us about planets and the birth of the universe. So let's all welcome her, the big man.
That was amazing. Unfortunately, now I have to do this other thing where I do a technological swap. But if you want to clap again when I'm done, that would be great. Oh yeah, there we go. Okay, no. That's so sweet. I had no idea you were going to do that. That's amazing. No, I'm kidding. That was a bad joke. By the way, there will be bad jokes in my talk because I didn't learn how to stop that when I became a scientist. So, before we start, to get us all in the right frame of... Okay, so close your eyes for a second. And we're going to go to the beginning of the universe. So in the beginning of the universe, it was incredibly hot and dense. You can imagine a universe that was nothing like what you know today. It was so hot that protons and electrons were separated, and electrons were swimming around and they were interacting with particles of light called photons. And those photons were bouncing off these electrons. If you open your eyes, you'll see an artist's representation of that time. Hot, dense, amazing, and actually pretty uniform everywhere in the universe. Now, as the universe cooled, those protons and electrons could slowly combine, and then the photons had nothing to bounce off of. So the universe slowly becomes transparent, and we see the radiation from that time, from about 400,000 years after the Big Bang. And that's what we call the cosmic microwave background radiation. But in order to tell you why you should care about it, I need to take you back in time from now, but a little bit further on from the CMB, the cosmic microwave background. So we're living in an amazing time. Here is a young photo of Einstein, because I know he liked to stick his tongue out and not wear socks, but I like the young Einstein because he was doing a bunch of cool science then. It's about 100 years, just over 100 years since Einstein published one of his theories of general relativity, which really is the bedrock of a lot of the work that I do. It's 50 years since the detection of that light from the early universe, the cosmic microwave background. And there are two guys standing in front of a giant antenna. Apparently photos were cheesy in the past. And this field has really grown incredibly. And in 2011, the Nobel Prize was awarded for the confirmation of cosmic acceleration. Now, the really cool thing about how science is a tiny field, physics is a tiny field, is I have met 4 out of the 6 men on this slide. The sad thing is that they're all guys, but I'm working on that. So one of the main things that really changed cosmology is using a connection between velocity and distance of certain objects and trying to figure out what that tells us about the universe. Thank you so much. No problem, thank you. It's hot in the early universe, so you can get thirsty. You guys are great. So this is trying to relate visually something that we know with our ears. So you live in Toronto, you have heard an ambulance coming towards you and the pitch of the ambulance increasing, and you've heard it go away from you and the pitch decreasing. So that's just Doppler shifting, and we all understand that. But the same thing happens with light. And so one of my colleagues actually, if you have a Connect and some code on the GitHub site that I linked to here, you can actually show this. So if we can play the video again. Oh, let's try and play that again. Anyway, so someone is twerking in front of a camera, and as she moves towards the detector, he's written some code that shifts the light blue, and as she moves away, it shifts the light red. And so this is like a visual, trying to make a visual analogy, because in the universe, we actually are measuring this red shifting and blue shifting of light, not of sound. But it's the same principle. So if you do that, if you measure how something changes in its color, either it gets bluer or redder, you can measure its velocity, either towards you or away from you. And this became fundamental. Oh, there we go, yeah. And in addition to that, you can measure the distance to galaxies. And so this plot, everyone always says it's Hubble, but he's only one half of this plot. He's the angry-looking guy smoking in the bottom left-hand corner. But the person who figured out this connection with velocity was someone called Slipher, Vesto Slipher. Isn't that a cool name? And Vesto Slipher measured this velocity of galaxies. So we had the y part of the graph, the up part of the graph, measured by Slipher, and the distances to galaxies measured by Hubble, and you put them on a plot, what do you see? This is the original graph from Hubble. One of my favorite things about it is that the line, the gradient, tells you something we call Hubble constant, and Hubble estimated Hubble's constant completely incorrectly. He said it was like 400 or something, and we know it now to be about 70 kilometers per second per megaparsec. But this relationship tells us that everything appears to be moving away from us, and the further away it is, the faster it appears to be moving away from us. And that's weird. It's strange and exciting. And a lot of people think, okay, well, if everything is moving away from us, what does that mean? You keep being told that we're not special, we don't live in a special time or a special place, so why is everything moving away from us? Actually, you can show that just by the expansion of the universe, it will appear that everything is moving away from us. And I'm going to do so with some very cheesy key point animation, because that's the way of the world. So, the universe in this slide consists of only 4 stars. I'm going to keep the pattern of the stars the same. But in the next slide, I'm going to double the distance between all the stars. I'm going to center on one star. So we're going to center on the top left and see what happens, okay? So I've just doubled the distance in slide number 2. I'll keep the original one on for reference so you can see. Oh, sorry, the middle one, okay? Now it looks like all the stars are moving away from the middle star. But all I've done is double the distance between them. And I can show you if I do the same thing, but now I center on the top left. It looks like they're all moving away from that star. And just if you need to be convinced one more time, we can do it on the bottom left. So just because the distance between everything else is increasing, it suddenly appears that everything is moving away from me. So this should help us realize that we aren't special. It's just the expansion of space that makes us feel special. In case you were having a good day. But this is important because it means that the Big Bang, or this expansion of space, isn't happening from anywhere particular. It's happening everywhere in the universe all at the same time. And in fact, I gave away the punchline a little bit, but if we think about time and distance, that means we're actually looking into the past. This is an image called the Hubble Ultra Deep Field, which is one of my favorite images in cosmology, because every thing that you see on this, except for 4 objects, is a galaxy. There are only 4 stars, individual stars in this image. Who can tell me which ones they are? Yeah?
The red one, the sort of with the cross.
This one? Yeah. Yeah, so this one, that one, and that one. And we know they're stars because they're so bright that they make diffraction spikes. So only bright things are bright enough to basically make the light bleed out and give you diffraction spikes. Everything else is a galaxy containing roughly 100 billion stars. So everything's not expanding from you, and you're not special because there are billions of galaxies in the universe. But one of the best things about this image is you can actually use this redshift idea that we discussed, where you can link the color of a galaxy to how far away it is, and we can actually split this up and kind of zoom through. So there are lots of scientists who are really into visual effects, and so they did this. They made a movie. It's going to start off quite slowly because we're close to home, but now you can see us zooming through this image where we've separated out the different components, the different galaxies, by their redshift. And you can see we're looking at different galaxies that formed at different environments in different times. We're really moving kind of backwards. And so when we look far away, we're actually looking into the past, which is just awesome. Okay, now obviously things get a lot fainter because telescopes can only look so far, and so we're often trying to push to look further and further away. Okay, so let's go back to the beginning. We know that everything is moving away from us now, and so if we reverse time which we can obviously all do in our heads, right? If we reverse time, it means that at one time, everything was closer to everything else. And if you do that all the way back to the beginning of the universe, you come up with the fact that the whole universe was inside the Big Bang. So it didn't happen in a point in space. The whole universe was inside the Big Bang. And we come to this, which is what we started with. This hot, dense, and incredibly uniform universe. There are tiny fluctuations in the density of things at that early time. In fact, the fluctuations are like 1 part in 100,000. Now, I really love analogies because I'm a scientist, and 1 part in 100,000 is like if you took a gallon of water and you put a drop of food coloring in. That's about the ratio of 1 part to 100,000. And the cool thing is that those density fluctuations, those tiny little overdensities and underdensities, places in the universe that are a little bit hotter, or a little bit more dense or a little bit less dense, they will clump together because gravity sucks. They will get more extreme, basically. Gravity makes you more extreme. So if you're an empty part of the universe, you get more empty and more lonely. And if you're a dense part, you just accumulate matter and you grow. And so these early fluctuations turn into all the stuff we know and love. Not cars, because that would be weird, but structures in the universe. And we want to understand what those fluctuations were like. So if we put the Big Bang here, we had this time, so very early times, it's very difficult to figure out because a lot of our mathematical equations kind of break, which sucks, but we're also working on that. We come to a time when the universe is cool enough for this radiation to travel towards us, and this is the cosmic microwave background radiation, which is a great tongue twister after you've had a couple of beers. And then the universe becomes opaque. So there was this period now, I told you earlier that protons and electrons combine and become neutral atoms. And light isn't bouncing off the electrons, so the universe is pretty opaque. And the universe is what we call neutral. But if you actually look around, most of the universe today is not neutral. Most of the universe is ionized. So for example, the gas in the neon lights, that's neon, those are neon gas, where you excite, you ionize the gas, and as the electron falls down, it releases energy, it releases light. And so a lot of the universe is like that. It's see-through. I can see all of you, which is awesome. And the reason why I can see you is because light is bouncing off your face. You are not making light in the optical spectrum. But the universe was dark for a while, and then slowly it became dense enough that stars started forming, and those stars got hot and they started to ionize the universe again. So understanding how this happened is one of the things we need to figure out, because we see galaxies quite far into the past, and we need to know, how did the universe go from looking like this to having galaxies in it like we know today? And then, stuff happens, and then we get to the present day, which is very exciting. And we're living here looking back and trying to figure out all of what the universe is made of. So I told you I care about the densities of this early time, but I measure light on the sky. So how can I measure light on the sky and turn that into something else? How can that tell me about what the physical conditions were like in the early universe? And the way we do that is by a really fundamental property of nature, and that is that the cosmic microwave background radiation is what we call a black body radiator. Okay, so what that means, what a black body radiator is it means that all I need to know about you is your temperature, and I can figure out exactly how much light you are giving off as a function of the wavelength or the color of the light. So here's a graph. On the x-axis we have the wavelength of light or the color of light. So highly energetic, short wavelength light is here, long wavelength light is here, and then we have like radio waves and stuff keeping on going. And if you just tell me your temperature, I can tell you exactly what this curve should look like. So for example, I told you I can only see you because you are reflecting light, but that's only because my eyes can measure optical light. If I had infrared goggles on and I looked at you, you would all be glowing at me, because I know your temperature is roughly 37 degrees. I'm not a biologist. Wait, isn't that when you die you have a fever? I don't know, some temperature. I don't know. Bodies are not my thing. So you have some temperature, and I can tell exactly what you should look like in the infrared. And so if I put on my goggles, I could find you, and that's exactly how infrared goggles and night vision works. And so, but you're not a perfect black body, because there are properties about your body to mean you don't radiate perfectly everywhere. But one of the things we know is that we expect this light from the beginning of the universe, we expect it to behave like a perfect black body, because it's just radiating from the early universe. Okay, so the one thing is I need to clarify temperature. So temperature in Celsius works great on Earth because we roughly have a good range of temperatures. But when we go to space, things get very cold very fast. And so we work in Kelvin, which is a temperature scale defined. So absolute zero is minus 273 degrees Celsius. And the maximum of Kelvin is very, very large. So great. So we know that the sun has a temperature of roughly, this is cool. Actually, this is one of my favorite things about the sun. It sounds kind of boring, but no, I love the sun. The sun is about 6,000 Kelvin. So look at that black body spectrum. Tell me where most of the light is coming from. Where is the peak of that curve? It's in the optical range. Isn't that cool? Because we see in the optical range. Isn't that amazing? No, it's evolution. So this is one of the most beautiful graphs. I really like graphs, but that's okay. You don't have to, but I do. So 50 years ago, there were these two scientists working at Bell Laboratories in Holmdel, New Jersey, which is near where I used to live. And they were not interested in cosmology. They just wanted to calibrate their radio telescopes. And the thing behind them is a telescope, because it's huge. Radio telescope, radio wavelengths. And they looked around, and they were trying to calibrate this receiver, and they looked in the sky, and they found that there was this weird hiss, and it was everywhere they looked in the sky, and they didn't know what it was. And they wrote a paper. They said that we tried to clean the pigeons out. There was pigeons, and actually they mentioned that there was a white dielectric substance, which is scientists speak for pigeon poo. Also, I'm foreign, I say poo. And they cleaned it out, and they couldn't get rid of this hiss. And they wrote a paper saying that they had this hiss, and instantly other scientists who had been looking for this realized that they'd been scooped, because they actually were searching for this. And this radiation had a perfect black body spectrum. So this curve is a measurement. It has error bars on it, but the error bars are so small that they lie under the thickness of the line. This was measured by the Cosmic Background Explorer telescope, and it's the black body spectrum of the cosmic microwave background. It has a temperature of around 2.7 Kelvin, so 2.7 degrees above the coldest thing possible. And it's awesome. Okay, so if you looked in the sky and you could see in the microwave, it's actually microwave part of the radio emission spectrum, you would see everywhere that there was this radiation. But we have other things to look at. And so how do we measure this radiation? Well, what we do is we first of all define what we call longitude and latitude in space. So we call it right ascension and declination because we want to give it a different name. But it's the same process. We project a sphere of essentially longitude and latitude in the sky, and then we unwrap it and you get maps like this. So next time you see a map like this, that's what it is. The galaxy is along the center. But what we're going to do is we're going to measure this light, and we don't really care about the average anymore. I care what is the temperature difference between this part of the sky and that part of the sky. And the reason why I care is, imagine if I walked into this room and I did a survey of your favorite artist, favorite musical recording artist. And I know we live in Canada, but if every single one of you said Justin Bieber, I would know something was up. Okay? Sorry, Canadian joke. Because it's impossible, right? We have so many different cultures, ages, whatever. There's no way you would all say Justin Bieber. But I want to measure, as a function of how far away you're sitting, did you have time to talk to each other and figure out if you like the same music and maybe change your mind? And that's what we do. We measure the temperature in different parts of the sky. So visually, what this is we increase the contrast of our map. We take away that average. We keep taking away and making the contrast fine enough so that we can see those differences of 1 part in 100,000. And those are the maps that you might have seen. This is a map of the anisotropies, which means the parts that are not the same. Differences relative to some mean, temperature, in the sky. That's such a great picture. It's so great it made the New York Times. This is actually a photo of my New York Times because I had one. And this is a map made by the Planck satellite in 2013. So it had sent this telescope into space to make measurements of these temperature differences on the sky. And it told us incredible things about the cosmos. It wasn't the first one to do so. So the Wilkinson Microwave Anisotropy Probe, another tongue twister, in case you want to try that out later, or WMAP as we call it, also measured the temperature differences in the sky. And so this is really taking a photo of this early time in different frequencies. Okay, so first of all, you can see there is one big thing that isn't probably cosmological, and that's the galaxy in the center of the map. The cool thing is that the galaxy looks different as a function of frequency, and so we can actually remove that information to try and look behind it, to look around it, to try and figure out, I want to understand what is this telling me about the universe. Because those temperature differences tell us what is the shape of the universe, what are the different components of the universe. So this is the telescope that I work on. It's the Atacama Cosmology Telescope. We are super original because it's in the Atacama Desert and it does cosmology and it's a telescope. This is a photo taken by a graduate student who wasn't working hard enough. That's a joke. That's a joke. It's 17,000 feet. Or 5,200 meters above sea level. It's one of the highest observation sites in the world. I'm not allowed to go because you need a lot of actual skill to work there, like hardcore hardware skill. Apparently also any kind of simple addition is very difficult unless you have oxygen because it's so high up. And our telescope sits inside, so this is a ground shield. And the reason why we need a ground shield is because everything else is giving off radiation in the microwaves because it's colder. And so we're trying to protect the telescope inside from this radiation so that we can only look up. And it's very dry in Chile. So there's roughly the precipitable water vapor, or PWV, is around 0.5 millimeter a day. So there's very little moisture in the air. And that's important because we want to look out of the atmosphere and look to space. Oh, so here's a movie which my colleague made today. Let's see if it runs. And this is if you want to find us. So we're zooming in on the Atacama. We're very near the Bolivian border. And now you can kind of see inside the telescope, which is very cool. Okay, so great. I have this awesome telescope in the Atacama. What have I learned about cosmology? Well, we have a really pretty amazing idea of what the universe is made of. So we know that this stuff on the left-hand side, everything you know, stars, gas, dust, me, you, it makes up a few percent, very small fraction of the energy of the universe. We know that 21% roughly is made up of what we call dark matter. And the thing about dark matter is that it's like normal matter, but invisible. And then most of the universe is dark energy, which is like nothing you know of. Nothing. So the majority of the universe is stuff we don't understand, which is why I have a job. And I'll talk a little bit more about that now. So my telescope basically goes to maps like this and cuts out small patches and observes it with even more precision so we can really figure out what's going on. And this allows us to realize what the universe contains. And one of the things we want to know is the universe flat? And I was thinking, I wish I could find a way to talk about the flatness of the universe and how it's dependent of the stuff in the universe. And then I realized I made a video about that. So I'm just going to play you a tiny bit of this video. Also, the animators are pretty cool. Oh, and you can't, there's no sound. Oh, excellent. I'll just narrate it. So Einstein did some stuff. And here, this is the universe, which is super cute. And we realized the universe could be shaped in a multitude of ways. So you could either be positively curved like a ball, negatively curved like a saddle, or flat. See, he does a little dance just now. Hey. Hey. And what we realize is that the stuff the universe contains affects its geometry. That's what Einstein tells us, that energy changes the curvature of space. And so if we measure what the universe is made of, that can tell us how flat the universe is. So we know that the universe has a telescope in it, and contains all the stuff we know, stars, gas, and we call that baryonic matter. Baryons are just objects like atoms or anything like that, neutrinos. And baryons are not as important as dark matter. And the reason why dark matter is dark is because it doesn't cast a shadow. So light doesn't reflect off dark matter. See, it's reflecting off a baryon, but it's not reflecting off dark matter. And dark matter isn't casting a shadow. Also, dark matter is in a bad mood, which is fine. But we measure dark matter because things are still attracted to it gravitationally. And that's how we can measure dark matter, because of its effects on other things. And we're hunting for, this is a fun part of the video, we're hunting for potential candidates, because we know that dark matter has to be a particle. It's just weakly interacting. But the majority of the universe is made up of this weird stuff called dark energy. It's like, aren't the animators awesome? Anyway. And dark energy has this weird property that as the universe expands, dark energy, we say that its density it's a constant. Okay? Now what does it mean if its density is constant? Well, if I took all the people in this room and I doubled the size of the room, the density of people in this room would go down, right? Because it's decreasing with volume. But if a cosmological constant is constant, it means as the volume of the room goes up, the amount of the dark energy has to go up to keep its density constant. And that's weird. We don't know anything that can make more of itself, not sci-fi not included. We don't know anything that can make more of itself as space increases. And that's what dark energy does. And so we actually use observations to measure this. So what do we know? We know that the universe is around 13.8 billion years old. We know that it has only a little bit of atoms, and the rest is dark matter and dark energy. We know that roughly the universe is scale invariant. That means that there are as many little blobs as big blobs. There are as many people as there are people-sized lumps in the universe, as there are bigger-sized lumps in the universe. It's a scale invariant spectrum, and we know that the first stars formed roughly 200 million years after the beginning of the universe. Okay, so in the few minutes that I have left, I want to talk to you about how we figure this out. So I am an observational cosmologist, which means I take data and I have to figure out how to use them to tell me about my models. And that means I take a lot of data and I do a lot of statistical processes. So how do I do that? How do I extract information other than pretty pictures from the universe? And I'm going to use it with analogies about me, because that's when you can in a public talk. We either measure the large-scale geometry of the universe, or we measure clustering, so how things are clumped together. So let's start with taking snapshots in time. Okay, this is me from the age of about 4 to January in Toronto. And if you take snapshots in time, first of all, apparently I change my hair a lot. And the places I'm in, I go from hot to cold, much like the universe, actually. But if you just looked at photos of me, you could actually learn a lot on average about what is happening in my life. And we can do that. We go to the universe and we take photos at different times in the universe. And one of the analogies we need is, you don't know that much about me, and so if we take a photo at any particular time, you couldn't figure out exactly what the time it was. You can only do relative time. But what we're interested in is actually, what if there was something that you actually knew how bright it was? Okay, so you're leaving tonight, and when you're walking outside, it'll be dark. Now imagine if the entire city is dark. And these are images that I took from a photographer, Jared Levy, who went around Manhattan during Sandy and took photos of the city completely dark. So this isn't photoshopped, this is actually New York City. But it serves as a really good example of what we're going to do. So if you wanted to cross the street and there are no street lights, what do you do? Okay, you're about to cross the street, you look and you see, are there any cars whose headlights are bright? If they're bright, you know you're going to be hit by a car, so you don't cross the street. But who taught you how to do that? If you've lived in a city long enough, you just know that, right? You just understand that there's a correlation between how fast, or how close an object is to you and the brightness of its headlamps. But that relies on a fundamental assumption. It relies on the assumption that you know how bright the headlamps were in the first place. The manufacturer has to put a certain brightness of headlamp in the car. If someone had fiddled with that, the chances that you get hit are much larger. And we do the same thing in the universe. We look out in galaxies and we look for objects that have the same intrinsic brightness. So this is a cool image taken of a galaxy, and it's beautiful, but the thing I care about is the thing conveniently located near the arrow in the image. So if you take your eye to the arrow and see, this is an explosion of a type 1a supernova. And in fact, it's supernova 2011 FE, in case you wanted its name. And the cool thing about these objects is we realize that they're roughly the same brightness wherever they are in the universe, wherever they explode. Intrinsically, they're roughly the same brightness. And that means I can use the difference between how bright they appear and how bright I know they actually are to tell me how far away they are. It's exactly like the headlamp analogy with a car, except it's cosmological. So you can think about it this way. I use this difference to measure actually the distance to these stars. And that tells me something about the way that space is arranged. Oh, that one's dying. That's sad. Oh. Okay. Cool. The universe just won't quit. Wow, it really doesn't like that, does it? So we can make a graph. So this is similar to the opposite of the graph I showed you earlier, which had redshift or velocity up here and distance here. We now just flip it around because we can. And these are measurements of these type 1a supernovae from a bunch of different groups. And that line is a theory curve that we might predict that we get from a theory like Einstein's theory of general relativity. And this allows us to tell just what the universe is up to. We don't want to only measure snapshots in time. We want to measure integrated measures. So you don't want to just know photos in my life, but you want to understand some properties of me that you kind of average over time. And so to make a real life example, I put the citation index of my PhD supervisor, because she's not here to yell at me. She's wildly successful. But this tells you, it doesn't tell you what she was doing in 2011 and 2012. It just tells you some integrated measure, how productive she's been since she got her PhD. And we do that in the universe. We measure these properties because as we are looking at the cosmic microwave background, we are looking backwards through all the stuff in the universe, right? But we know that that light from the cosmic microwave background, as it travels towards us, has bumped into like a bunch of galaxies. And as it bumps into a galaxy, it'll be kind of distorted because of the matter in the galaxies. And so we can actually figure out, as the light hits us, can we figure out how many times it's been distorted or what happened? So that's an integrated measure. So we call this lensing. This is really cool. Next time you break a wine glass, don't throw the end away. File it down, because no one wants a bloody hand when you do this experiment. But if you hold it up to something, you see kind of rings, right? The smearing out of light. The same thing happens in space. Galaxies do that. Because of Einstein's theory of GR, matter distorts light around it. And so galaxies actually bend light. And so we can measure how massive the galaxy is. This is a much smaller effect. So I'm going to show you a little movie of the CMB under the effect of lensing. And I guarantee you if I didn't put the little word there, you wouldn't know which one was which. Neither would I. So these are tiny, tiny fluctuations, but we use that to figure out what stuff is bending all the light. Another thing we can do to try and figure this out is to measure as a function of position on the sky, spatially, are things correlated? So if there's a galaxy there and there's a bit of lensing there, I can think, okay, maybe that galaxy did the lensing. So in order to illustrate this, I used data from the US Census. Any statisticians, I tried the Canadian Census, but you don't have nice graphs. You just have like a PDF, and that's not cool. So I put up this graph of, I pulled this up of the percentage of households that had female kind of breadwinners, okay? And so they're colored darker, the higher the percentage of the households that have female breadwinners. And then I made another map of the average family size. Okay, and I want to see, is there any correlation? Okay, I can do this by eye. It's a fun game to play, especially if you're trying to line up the images for a talk. And you can see, okay, we can find out some correlation statistically. But another thing that you notice straight away is here I made 5 bins for both of them. What if I only made 3 bins? So suddenly the data gets a little bit more blurry and not really sure spatially what's going on, and you learn a little bit less from the correlation. So we can do this, and that we do exactly the same thing in space. We measure light from the cosmic microwave background, which I talked to you about. Then we measure the distribution of galaxies on the sky. So this is a map from the Sloan Digital Sky Survey. And we cross-correlate them spatially. We literally say, what's happening if we take those 2 maps and put them kind of at the same place in the sky? Can we learn anything? And we did, and in fact, a fantastic graduate student, Matthew Madhavacharil, who's coming to do a postdoc at the Perimeter Institute in Waterloo, did this with my group, and we measured the lensing that dark matter halos is doing to this cosmic microwave background. This is the plot. I just put it to show you, but it's much less exciting than the cool image. But here you actually see where there are galaxies. If I go to the position of a galaxy on the sky and I put it at the same position as the CMB, on average, you see that there is this effect, which is kind of cool. Okay, so we're coming to the end of the talk. I know it's warm in the room. What's next? I've told you about what we're doing. What's next in our field? What's the exciting stuff? Well, a businessman and philanthropist and scientist, Jim Simons, gave $40 million to collaborators of mine and my group to upgrade our experiments in the Atacama. So there's the telescope, the Atacama Cosmology Telescope. There actually are also a bunch of other telescopes around. And we're going to soup this up and keep doing this research, but improve the actual technology, the detectors, and all the instruments that we use. And I'm hoping to get the University of Toronto to be part of this collaboration, which is pretty exciting. On the side of the supernovae, we are building something called the Large Synoptic Survey Telescope, because apparently acronyms is all we do in science. And it's also being constructed in Chile because it's a very good site. You can see the strange humanoid. So this is a giant telescope, but no one wanted to call it that. And we're going to measure scan the sky once every 3 days. So we're going to be able to measure these supernovae incredibly. Just to kind of put this in perspective, this is going some photographic plates. This is an image of the sky taken with photographic plates. This is what it looked like. We're going to focus on this galaxy because it's going to show us how cool LSST will be. If we go to the Sloan Digital Sky Survey, which I mentioned, this is kind of like one of our best things currently. That galaxy looks pretty neat. If we push a little bit further into a deep lens survey, which is great, but only looks at a very tiny part of the sky, that galaxy gets clearer. And LSST will give us the same kind of image, but over the entire sky that you can see from Chile. So we're going to get an incredible amount of data. So to put this in context, I'm going to use yet another analogy. Isn't that a cool fish? Okay, so imagine if all of those supernovae that I told you about, all of those exploding stars, we have detected to date about 4,000 of them. And we've been studying them since the 90s. And then, to remind you, the Nobel Prize for Acceleration was given to people doing this work in 2011. So we have about 4,000. And you can say, let all the supernovae be a fish, okay? LSST will give us 10,000 candidates per year for 10 years. So we'll go from 4,000 that we really knew very well to 1 million. Now, that's cool if you like fish and or supernovae, which I do. But the problem is that not all of those are going to be the ones that are useful. There are going to be some supernovae out there that have the equivalent of dodgy car headlamps, right? That aren't going to be able to be useful for cosmology. And I need to figure out which ones they are so I can root them out. And that's where statistics comes in. So luckily I use a lot of statistical methods to actually try and figure out which are the fish that I care about. Because like that guy's not useful at all, obviously, right? No, I'm kidding, I don't know. I think those are all the same kind of fish, actually. So we use new technologies, new equipment, new statistical methods, and we're really continuing to push the boundaries of understanding a bunch of different parts of the universe. I don't only do one thing. I'm interested in how the universe started, how it's changing with time, what it's made of, and ultimately how it's going to end, because all of these things tell us something about the eventual fate of the universe. And as things progress, we get more data, and what that means is that we have to get better at our statistics, but also it allows us to ask more questions. So my job is asking questions, and right now, that's your job too. Thanks.
So if you have questions for Renée, just raise your hand and we'll choose you out.
Sure.
So you said that at the beginning you talked about the Big Bang, right? What was there before the Big Bang?
It's a great question. The question was, what was there before the Big Bang? And the answer is cheese. No, it's not cheese. Okay, you're tired, I get it. I got the most in the beginning. No, the thing is, we don't know. So, in the sense of, all I know for sure is that at some point in the universe was very hot and very dense and very small. But exactly what the physics of how that happened, we actually can't go back all the way to there. So from about a second after the beginning of the universe, I can basically tell you what happened. We got that nailed. But that first second, we don't know. And the reason why we don't know is because the maths gets hard. So what was there before the Big Bang? In my mind, I define the beginning of the universe at the Big Bang. But there are other theorists that say they don't like that idea. And so they think, okay, what if before the universe there was just another universe that was bouncing and colliding? And they call this the ekparodic, or the bouncing cyclical universe. So I don't really know. But that's a good question, and you should keep asking the question. Yes?
So if you took your thermal imaging scan on all the people here, my theory is people are made of different types of atoms. So you could probably find one or two people in here that are made of dark matter.
There's dark matter in this room, which is kind of cool. There is dark matter, we believe, everywhere in the universe. But the reason why dark matter is so interesting is that it doesn't interact with us. So if we replace the sun with dark matter, other than the fact that there was no sun, you wouldn't tell, because gravitationally it still interacts exactly the same way. And so we build these mines filled with very heavy water, and we look for one interaction between a dark matter particle, potentially, and a normal atom. And occasionally there'll be a flash of light. And so there are searches for dark matter all the time. Yes?
So you mentioned using statistical methods to kind of root out the kind of supernova that aren't used for this. Because I know now they talk about exoplanets and they use statistical analysis to get on
Sure.
things. Like, what kind of methods do we use to kind of determine what needs to be rejected?
Yeah, so I had a slide about that, but then I thought everyone would get scared. No, so I use actually Bayesian statistics. Oh, the question to repeat for the recording is, what statistical methods do we use to separate out different types of supernovae? And so let me, at least for the sake of people who care about stars that just just explode at the end of their lives anyway, they are very interesting. They're just not interesting for cosmology, but we want to separate them out, and we use Bayesian methods. So let me use an analogy which I really like. If I told you that I arrived in this room today via dragon, okay, you'd know I was lying, or you'd think that was incredibly impossible. But if the only data you have is that I'm standing in front of you, then if I tell you I came on foot or on dragon, if all you use is the fact that I'm here, you have no way to decide. So how did you know that could not be true? What you used is your prior assumption as to how likely dragons are anyway. If this was Game of Thrones, this would be a whole other conversation. Actually, I don't watch Game of Thrones, so are there dragons in Game of Thrones? Because I don't know. But you used your prior. And so that prior knowledge of how likely dragons are to exist in this or any other world is really important to make this decision. And so I use that prior information to separate out the different types of data. Yes?
This question came up in the last lecture as well. Dark matter, its density does not change, even though the universe is expanding.
Dark energy.
Dark energy.
Dark energy.
Right. So, again, like, what is your explanation for that?
Yeah, no, I mean, I joked that it's the reason I have a job, but we are trying to understand the nature of dark energy. So the difference between dark matter and dark energy is dark matter we think could be a particle, a thing that is weakly interacting with light, but that has normal gravity and stuff. Dark energy, we literally have very few even hints of ideas as to what it could be. It's acting like anti-gravity. Imagine if I threw this up and instead of falling on the ground, it just floated away. That's what dark energy is doing. It's acting against everything we know to be true. And we don't know. So what we do in cosmology is I measure its properties. I measure its density. I measure its pressure in space. And I measure what is it doing to the expansion of the universe. And I try and figure it out. People come up with models. So I have a model for a type of particle.
It's the same, is that?
Its density remains the same.
Right.
Yeah.
The density remains the same.
Exactly.
So,
exactly. So people have models. People can propose a model. So I have a model called an axion, which is very cool. And we say, what does the axion do? And then I confront it with my data, statistically check, and then if it's good, great. If not, but at the moment we don't know. And I think the person who figures it out will win just all the prizes. Let's have a question from the lady in the denim. Yes.
It's actually a follow-up. So I noticed with the fact that dark energy doesn't change density. What are the repercussions of that?
Oh, so the question was, what are the repercussions of the fact that dark energy doesn't change its density? This is super cool as a question. So, we live at a time very close to when there was more dark energy than other stuff in the universe. So we've now got 25% dark matter and 70% dark energy. That's kind of close. But we know the property of dark energy is the more space expands, the more of it there is. And so for most of the future of the universe, we know there will be more and more dark energy. And so the ratio of dark energy to everything else will increase. In fact, it will increase kind of exponentially, which means in the future of the universe, it's going to be only dark energy. So the stars will run out of fuel and they'll just die and we'll all be gone. And there will be black holes. And those black holes eventually with time will evaporate. So the universe is going to be just dark energy and it's going to be huge forever. The cool thing about that though is that it's going to happen like way after the Earth gets burnt by the sun. So we're good. Yes, gentleman in the like grayish. Sorry, behind you.
I was just wondering if there's any other manifestations of dark energy apart from the expansion of the universe, or is that?
Yeah, that's a really good question. So one of the things when I bring up dark energy, people are like, "Well, I don't know. That seems a little weird." If it's only these supernovae, you could just say that it was rubbish, right? The problem is, unfortunately, is we now have independent evidence for dark energy from supernovae, from the cosmic microwave background, from that lensing stuff that I talked about, from the way galaxies cluster on their own and clump together. We have all these different independent suggestions of dark energy. And so we can't just explain it away with some weird data. We can maybe explain it away with some modifications to the way gravity works on very large scales, but that isn't necessarily more attractive. Yeah. Now, gentleman in the red, sorry.
So when you mentioned the expansion of the universe,
yeah.
Is the expansion at the galaxy, between galaxies,
or
within the galaxy, or the space between you and me?
That's a great question. So is the expansion between you and me, is it the expansion between the galaxies? Where is this expansion? And the way I like to think about it is, we talk about gravity being like such a cool force and really important. Gravity is totally not the most important force on my body. The most important force in my body and your body is the electrostatic force, which keeps your atoms from flying apart, right? Because they should fly apart. Gravity only matters if I jump off a building, right? No, I mean, like, it's not important. I'm not exploding, because that's what would happen if the electrostatic force was not there. And so it's a function of scale. If I look at you in the humanness then electrostatic force makes more sense. If I throw off a building, gravity makes more sense. And so if we go to the very largest scales, galaxies will be interacting between themselves, and so they will collide as normal. This is only going to affect much bigger than that. So really the clustering between things, the biggest distances we know. And that's of course what makes dark energy hard. If dark energy affected this, I'd be able to detect it much more easily, or figure it out much more easily. So it's only affecting the universe on the largest scales. The problem is, as everything else runs out, we're kind of stuck with it. And so the largest scales will be dominated by dark energy eventually. Yes?
I was wondering, there's a lot of talk about like finding dark energy. Is it possible that it's just intrinsic, like law of nature of how space works? So instead of it being a thing that's affecting space, it's just space naturally expands by itself.
Yeah, so the problem is that, you know, I said gravity sucks, which is, even though it's corny, is a really useful thing, because if I think of the way we thought the universe was supposed to go, is the same way, you know, you throw a ball up and it falls down. We expected the universe would start expanding, and then eventually the gravity of everything inside the universe would pull on everything else, and it would stop expanding and it would contract into some kind of big crunch. That's what we expected to happen. So the fact that the opposite is happening, that everything is accelerating faster and faster, I can say, oh, there's a scalar field that is doing that, which is fine, or I can describe it in nature. But as a scientist, why did it switch on? Why did it happen? You know, I'm not happy to just say it's the way space works. I want to really test it. So one of the things that we do, I said we can explain dark energy a little bit if you say, let me change the laws of nature on big scales, fine. But as a scientist, you need to tell me what makes that model different from just a dark energy thing. And then I spend my energy testing the difference between them. So basically ruling out models and ruining some scientists' day, that's my job.
So we have time for one more question for Renee.
Yes?
You mentioned that there was some slight variations in the density of the early universe. So do you know why there was variations in density? Why could the early universe not be perfectly uniform in density?
It's a very, very cool question. And in fact, yes, I will repeat the question, sorry. The question was, I said that there were differences in the density of the universe at early times that were tiny, 1 part in 100,000. But why? The question was, why was it not perfectly uniform? And that's a fantastic question. So we believe that those fluctuations were laid down, that they're actually quantum fluctuations. So at this early time, the gentleman in the front asked about this early time and what was before the Big Bang. That stuff was really quantum physics. And we believe that those fluctuations were put down by quantum interactions, quantum physics. And so studying exactly how that happened is one very active part of research. But it's really the natural kind of frothing of space at those early times became and kind of grew to be the macroscopic things we see today. And the reason why we expect that to happen is because we think that the universe has a quantum-like nature. And so these fluctuations will be there. Thank you.
Thank you for all your research.